This is the video that goes with the Solubility Lab. The concepts in the Solubility Lab are discussed in your text in Chapter 8, the chapter about solutions. There's a list of vocabulary words that I would recommend that you review before you start the lab. You can look in the introduction to get their basic definitions, or if you want to look more, you can look in your chapter. So the words that are important to understanding the lab are solute, solvent, solution, homogeneous mixture, then we have soluble, insoluble, miscible, immiscible, saturated, unsaturated, electrolyte, I'll come down here, non-electrolyte, and finally the rule that you might want to review is like dissolves like, which really in one form or another answers most of the post-lab questions. And we'll talk a little bit more about it when we get to that section. So let's start the lab and take a look at the data that was collected. So I did this lab. This lab is really based on a lot of observations, or what we call qualitative information. There are no numbers or quantitative information. Unfortunately, photographs can't give you a perfect sense of this, but I'm hoping it's going to give you enough sense that you understand what's happening. So part A I usually do as a demonstration in lab. It's called electrical conductivity. So we're looking at how different solutions can conduct electricity. And substances that conduct electricity are called electrolytes. Electricity, I ran out of room. And then non-electrolytes do not conduct electricity. So I'll just say don't conduct. Now, what makes a solution conduct electricity are ions. So electrolyte contains ions. So remember, ions are charged particles, plus or negative, and we can usually identify these types of substances because they will be ionic, or they'll have metals and nonmetals for the most part. And so what we're looking for is if a solution will conduct electricity. And we use an electrical conductance apparatus, which you can see in the photograph. Now it looks kind of archaic or very, very old, and it is, and so that's one of the reasons that I do this as a demonstration. So if you think our light bulb is a filament, so it has a little filament here, and then there's wires underneath this, and then there's wires that come in this tube, and when you get here, there's two electrodes that are far apart. And so we have wires going into the test tube. So it makes like a circle. But when there's no solution and these two electrodes are far apart, the electricity can't get anywhere, and so the light doesn't go on. But if I put it in a solution that has ions, the electricity goes through here, it goes up here, it comes around, and it can go in between the two electrodes. It can skip them because the ions that are in the electrolyte carry it back and forth. So what we're looking for in our lab to determine if a solution is an electrolyte or a non-electrolyte, we're trying to see if the light bulb will light up. Because if it does, then we know that there's ions in the solution and it can conduct electricity. Now, I think it would be very helpful if you don't already have your procedure out so you can kind of look along as well as get your data page, and specifically for part A, the electrical conductance. So as you look at the pictures, you can write down what it's being asked of you. So if you look, what we're going to be looking for, it says here, okay, so it says strong electrolytes will almost completely dissociate to form ions and causes the light bulb to glow brightly. Weak electrolytes, that would be the other one, do not contain very many ions and the bulb will be dimly lit. Okay, and then what else does it say? A non-electrolyte does not contain any ions, so the light bulb will not give off light. So what are we looking for? I'm going to underline it so I can see it better. We might have a strong electrolyte and it will glow brightly. A weak electrolyte and it will be dim. And then a non-electrolyte with no ions will not give off light. And how we're going to identify it is to have a 0 through 5 number. Now, so I would anticipate normally in class, if it's a 0, it means there's no light and everybody should have zeros. If it's between a 1, 2, 3, 4, 5, people's numbers may differ because our eyes interpret the brightness a little bit differently. So 0 will be no light. We should all match there, but the higher numbers, I might think it's a 5 and you might think it's a 4, and that's fine. Okay, so this first one, and I have the label here, this is distilled water. And it's really hard to see, but there's a wire in the light bulb and it's not lit. So this has no light. Now, I'm not going to give you the numbers for all of them, but just as a starting, I would say this is no light, so that would be a 0. Now, this second one, I had to turn off the lights in the room. If you look at the light bulb, there's a glow, and I'll outline it, then I'll erase it. The wire inside this, right where I drew, is glowing. Let me erase it. Okay, so it's glowing, and it's not very bright, so it's a dim light. So I'm going to say a dim light, and I'm going to give it a 1, and you might think it's a 2, remember. This is for tap water. So what's the difference? Distilled water or deionized water, that's pure water, and pure water doesn't have ions, so it doesn't glow. Tap water, on the other hand, has water, but it also has other things. It could be from the pipes or from the source or from the treatment, and it must have a small amount of ions because it has a dimly lit light. So distilled water, the first one, is a non-electrolyte, and tap water would be a weak electrolyte. So let's look at the next example. So this example, you can see the light bulb is glowing much different, and this is sodium chloride. So this is NaCl. Now the difference between the two is their concentrations. This one has a 0.1, and this one has a 1. So this is 0.1, and the capital M is a concentration called molarity. You'll do more with that in chapter 8 as well. And then this is 1 molar. No, maybe chapter 9. Nope, chapter 8, sorry. And this is 1 molar. So the one on the right, this one has more concentration. Now, if we look, both of these light bulbs look very, very bright, which tells me they have lots of ions, right? Because it's ions that make it conduct electricity. I really can't see the difference between the two, and so let's say I might say that this would have a 5. So this is bright light, which means it's a strong electrolyte. And I might give it a 5. Or you could even say, well, I'm going to give it a 4 because I don't know if it's the brightest. And that would be okay. I'll give this also a bright light. I'm going to say this is a 5. Now, I will tell you there is a limitation of my little light bulb because, light bulbs can only get so bright. So it could be if my light bulb could get brighter, that the one on the right, the 1 molar, that one maybe could get brighter, but my light bulb can only get so bright. But sodium chloride, which is an ionic compound, has lots of ions when it's in solution. And so this is a strong electrolyte. Okay, now I'm going to show you, but I want you to pick your numbers. Okay, so this one here, if you look here, this is 0.1 molar sucrose. And this is 1 molar sucrose. So it's more concentrated. Now sucrose is C6H12O6. And, hold on, maybe, let me correct myself. That's glucose. Oops, under race. They all have, what they have in common is they have carbons, hydrogens. So it's C12H22O11 is sucrose. That's an 11. It's just, both sucrose and glucose would do the same thing. They're carbons, hydrogens, and oxygens. There's no ions. And how can I tell there's no ions? There is no light. Right? No, not the wire's not even lighting up. No ions. This is a non-electrolyte. And now on this example, you can see what I have here. I have HCl. So this is 0.1 molar HCl. And this is this is 1 molar, the more concentrated one. I will tell you it does have ions, and how do I know? Because the light is very bright, so it would be a strong electrolyte. You choose the numbers. You've got to write the numbers between 0 and 5. And then finally, and this is really my favorite one to do in class, this is 0.1 acetic acid. And this one is glacial. Whoops, I think I have them backwards. This should not say glacial. That's my fault for the lab. I thought about it when I didn't change the label on that one, and I should have. This is glacial acetic acid. Acetic acid. And this is pure. So this is acetic acid, which is the acid that's in vinegar, and glacial acetic acid is pure. Now this one, the label should read 0.1 molar acetic acid. And what you have to do to get a lower concentration is add water. And it's really, I think this is so cool. So look, when I make a mixture and I dilute it and add distilled water, so the water doesn't add any ions, now it creates ions. And this is an example where acetic acid, which is CH3COOH, I added water to it and it reacts. And it makes CH3COO with a negative and H3O plus. Now I know that it doesn't do this very much because there's not very many ions. I can tell because the light is dim. But I think it's really cool to see that sometimes when you dilute or make a mixture by adding something like water, you get ions. So a glacial or pure acetic acid is a non-electrolyte, but the 0.1 molar acetic acid is a weak electrolyte. And again, before we leave this section, remember, an electrolyte is a substance that conducts electricity in solution because of the presence of ions, plus or minus charge. A non-electrolyte is a solution that does not conduct electricity because it does not have the presence of ions. So back to that thing I said, electrolytes may make you think of Gatorade. Gatorade contains substances that have ions. Our body needs ions for our nervous system to work properly, for example, with our muscles, including our hearts. So if someone sweats profusely, vomits, or have lots of diarrhea, they lose a lot of fluids, and those fluids contain electrolytes or ions that our body needs to function properly. So things like Gatorade can replenish those if too much are lost. So now let's take a look at Part B. You can turn your data to Part B as well as your procedure. Now what we're going to be doing is looking at the solubility of solids. Now the two words we're going to use to describe what's happening are soluble, and this means that the solid that I put in the liquid dissolves, and insoluble. And insoluble means that the solid does not dissolve. In this experiment, if you were doing it in lab, I'd tell you be very careful not to saturate your solution. A saturated solution means that it has all of the solute, the substance that it's dissolving, that it can hold. And when a solution becomes saturated, it no longer can hold or dissolve any more solute, and so the solute just sinks to the bottom. This is deceptive when we're trying to figure out if something will dissolve or not, because we think it won't dissolve, but in truth, it's just not dissolving because we've added too much. Maybe you've seen this happen if someone you know or you yourself has made sweet tea and you add so much sugar that it just settles at the bottom. It doesn't mean that no sugar has dissolved. It simply means that so much sugar has been added that the solution is saturated and it cannot dissolve any more of the sugar. And we're looking for unsaturated solutions. Unsaturated solutions can still dissolve more solid. So if we're trying to see if something can dissolve or not, we want to make sure that we haven't added too much of the solute. So I had test tubes, and what we do is we're going to take 4 different solutes. So the solutes are in the smaller amounts, and this is what we're dissolving. So here's our solutes, and we're dissolving our solutes. And then what we're going to do is we're going to add it to 4 different solvents. And in our solvents, we will have the first one we test is water. Let me see. To each tab, add 3 milliliters of water. So in this case, this is my first solvent. It's what I'm trying to see if it will dissolve in. And then if you look down here, I had 3 more solvents. I had ethanol, acetone, and petroleum ether. So what we're looking for is if the solid dissolves. So I took a small amount of solid. Well, let me describe by looking at table salt. All right, so this first picture here, I'll label it picture 1. I had sodium chloride, table NaCl, and you can see I took a very small amount and put it at the bottom of the test tubes. Then I measured out 3 milliliters, and I didn't show you all those steps because it just was taking too many pictures. So I added water. So this is, all of these are with water. Test tube 1, this is test tube 1, this is NaCl. And NaCl in water, you can see that it dissolved. And now the second one, and I'm looking here to see if I got, because, oops, this is NaCl. Let me look. All right, so I made a mistake in my description of this, and I apologize. I caught myself when I got there, and I apologize. So let's take a look at this again. So all of these have NaCl. That's what they all have in common. I had backwards in here. So this is NaCl in water. This is NaCl in ethanol. And I'll tell you how I realized my mistake before I got any further. This is NaCl in acetone. And this is NaCl in petroleum ether. Now it really is hard to see, and I tried to do the best I could with pictures. But if you look, NaCl in water, which we should know from our life experience, this one is soluble. And I'm going to work all right on the first one with you, and then I'm going to have you do the other ones together. On your own. So NaCl, I see if you look in here on picture 1, this is test tube 1, there's no salt left. Now this is ethanol, and if you look closely right here, there's still salt. Now what I did was I added 3 milliliters to each one of them, and I let them sit for about a minute or so. Then I took a stirring rod and really tried to stir it to see if I could get it dissolved. And so this one did not dissolve, and so in ethanol it's insoluble. And then this is number 3. And again, I'll show you where you're looking. Right down here, do you see that solid? So I tried to get it dissolved, and it wouldn't. So we say that that is insoluble. So when the solute does not dissolve in the solvent, it's called insoluble. And then petroleum ether, again, I see solid there, and it's called insoluble. So let me talk about this rule, like dissolves like. How can we predict what's happening? Well, like dissolves like is the rule. Like dissolves like. And what this rule means is that substances that have similar polarities will mix with each other. Okay, so of the solvents, what I can see is, well, I know water is polar and sodium chloride is ionic, and so they must be similar, so they dissolve. The sodium chloride, this is ionic. Okay. Ethanol is what we would call a nonpolar. And salt is ionic. And so, though ionic and nonpolar are not alike, so they don't dissolve. So salt, again, is always ionic. So it would be ionic the whole way through. And both acetone and petroleum ether are nonpolar. So the rule, like dissolves like, means that things that are not similar will not dissolve, and things that are similar will dissolve. So ionic substances must be similar to polar because they dissolve, but it's not similar to nonpolar. So let's take a look at the next one and see if we can reinforce this idea. It's not an easy idea, so don't worry if you feel a little confused. So the second one, let's look at this one. So this is, you can see here, sucrose. So that is the solute. Okay, that's what I dissolved. And so I have 4 test tubes, and this is 1, 2, 3, 4. And so this is with water, ethanol, acetone, petroleum ether. Now, we know from what I told you before, water is polar. Ethanol will be nonpolar, nonpolar, nonpolar. Sometimes ethanol, well, we'll talk about it. Sometimes it almost wants to be polar. So chemicals can be odd. Now, sucrose is C12H22O11. And these oxygens right here make sucrose polar. So if sucrose is polar, we have polar and polar. There is nothing there. It is soluble because like dissolves like, polar and polar. Now looking at the others, their solid remains there, so it's insoluble, solid, and solid. And this makes sense because the general rule is like dissolves like, but polar and nonpolar are not alike, so it doesn't dissolve. Right? Like dissolves like. So polar dissolves other polar substances, and nonpolar solvents dissolve nonpolar, but nonpolar won't dissolve polar. The third substance is naphthalene, and you probably were glad you weren't in class for this one. This smells like mothballs. You can see I used very little. And let's see. So this was with the water. This was with ethanol. This was with acetone. And this is with petroleum ether. Now looking, it was hard for me to get a picture, but there's white solid in there. Okay. This is the only one that had white solid. The other ones did not have any solid left. Now I'm going to have you guess. I've told you already multiple times, two times. This is polar. This is nonpolar. This is nonpolar. And this is nonpolar. So if like dissolves like, if naphthalene did not dissolve in water, it must be the opposite of what water is. And if naphthalene did dissolve in the other ones, then it must be what? Question mark. Now the last one, again, I wish we were in lab to see this because I think that you would think it was cool. This is iodine, and iodine is one of the few nonmetals that are shiny solids. I held it up there so you could get a glimpse at it. I used really just one little teeny tiny crystal in my examples. And I had water, ethanol, acetone, and pet ether. And iodine has a formula of I2. And diatomic elements are nonpolar because, remember, nonpolar means that they share the electrons equally. So two iodines would share equally. So if you look, this one is the only one that has solid. Notice the water really didn't change any color. It still is colorless. But in the ethanol, the acetone, and the petroleum ether, there was no solid left in those test tubes. And I tried to shine light on it and get it so you could see it a little better. But the colors are so dark it was hard to see. But I will tell you there is no solid left in ethanol, acetone, or petroleum ether. The water is the only one that was insoluble that had some solid left. And you can see even the color of the water remains colorless, while the other ones all changed color. So as you go back and look at the results, and you can go backwards if you need. What you're trying to do is record if the solutes were soluble or insoluble in each one of the solvents. Keeping in mind the rule like dissolves like. which means polar substances will dissolve other polar substances, and nonpolar substances will dissolve other nonpolar substances. However, polar substances and nonpolar substances will not create a solution. They will not dissolve each other. Now the last part is about mixing liquids. And now we do change the word when we talk about mixing liquids from soluble and insoluble to miscible and immiscible. So when two liquids mix, then we call those liquids miscible. When two liquids do not mix, we call that immiscible. Oftentimes, when liquids do not mix, they will form layers. And so we had 3 test tubes that were to be put together. We have water and an alcohol called isopropanol, water with hexane, and isopropanol and hexane. And the formulas behind the names are just their formulas. What I can tell you, just as a general rule, just a knowledge, well, I always remember that water is polar. And that's one of those things that I keep in. I don't like that color, sorry. There, let me get a different color. Water is polar. And I just keep that in my toolbox. Because when I'm trying to decide if things will mix or not, knowing water is polar helps me a lot. I can also tell you that things that only contain carbons and hydrogens, like hexane, are nonpolar. So if you have a substance that only contains carbons and hydrogens, it's called a hydrocarbon. And these are always nonpolar. So if I were making a prediction, I would tell you that test tube 2 that has water and the hydrocarbons, that they are going to not mix. Why? Because water's polar and hydrocarbons, which is like hexane, is nonpolar, and polar and nonpolar don't mix. Now this isopropanol I might have a little question about. It does have carbons and hydrogens, but it also has an oxygen and a hydrogen. And oxygens and hydrogens, they like water. So it might mix. It looks like it could have both properties. So this is a question that the experiment will help us answer. So let's take a look. So this is the first one that I did. And this is water plus isopropanol. And if you look, it just looks like one liquid. It mixed completely, so we call that miscible. And this is test tube 2. And this was water, which is polar, and hexane, which is nonpolar. And if you look right there, it's like oil and water. There was a layer. So these do not mix. They form layers, and it's kind of hard to see with 2 colorless liquids, but there's a little layer in between, like oil and water. And so this we would say is immiscible. Now, one of the questions says, well, what is what? So I added more water. To this picture. And if you look, here is, right there is the layer. So which layer got bigger? The bottom layer or the top layer? So I would say this one got bigger. And so if I added water and the bottom layer got bigger, that would mean water is on the bottom because it got bigger. And then hexane is on the top. Now this is the last one, and it has, this was isopropanol and hexane. And there is no layers. And so you write your observation there. And just to show you what it looked like when it was all finished, here are all my solutions. We had the NaCl, we had sucrose, we had naphthalene, we had iodine, and then these are the 3 liquids that we just did. So this is ionic, this is polar, this is nonpolar, and this is nonpolar. And remember, we used 4 different solvents on these. And so as you go through this lab, I want you to try to process in your mind the idea of like dissolves like. All right, please feel free to ask if you have questions, or maybe you'll run ideas by each other. Have a good day. Bye.